So thank you very much to the organizers for letting me speak. It's a bit of an anti-climax because I think I'm following Alex Lavosky and Akira Furusawa, who's showing you these fantastically complicated continuous variable experiments. And today I'm going to talk to you just about Homodyne detection. I'm going to talk to you about integrated Homodyne detection in silicon, and hopefully the reasons for why I might want to do that become clear as we keep going. So I would be remiss in my duties if I did not precede my talk by at least one advertisement. I'm a lecturer here in the Department of Physics, but also in the quantum engineering CDT we have here. So this, for those of you who are unfamiliar with the CDT, this is sort of a one-year training program that our doctoral students go through before they start their PhD with their new supervisor. Why am I talking to this? Why am I talking to a room full of professors about a doctoral training center? Well, so we have a few different ways that professors can engage with the CDT. One of which is coming up very soon. During their first year, they do 2 3-month research projects with 2 different supervisors. So if you're at all interested in perhaps getting a CDT student to work on a project of yours, we have the Project B, which is the second of the 2 projects, and we're advertising the call sometime next week. Okay, so Homodyne detection, why? I feel like this slide is maybe a little bit redundant given the 2 previous talks, but I'll go through it anyways. So we know that, or at least we may know that Homodyne detection is useful for characterizing states of the quantum electromagnetic field. Okay, so we use this on things like Fock states and squeeze states, non-classical states that are going to be useful for all types of very important quantum information protocols. So we just saw an example of this in Akira's talk. Also some other work that I wanted to mention is that it's useful for something called coherent state process tomography, which is using sort of coherent states as well as these Homodyne detectors, which I'll talk about in a moment, but you'll learn that they're sort of made of classical bits to construct a quantum measurement. So we're using something like classical detectors to make quantum measurements. Okay, so why do we want to make this integrated? Well, there's all sorts of reasons for this, but some of the main reasons are that we have things like single photon sources, and hopefully in the future we will have things like squeeze states on chip. And so every time you couple onto or off of a chip, those of you who are in integrated photonics, you know you undergo quite a bit of loss, okay? And loss is a big problem in continuous variable quantum optics. The reason is, as we heard in some of the previous talks, you can model loss with a beam splitter, where you throw away the lost, the reflected mode. Okay, and then we also know that there's another mode of the beam splitter, and through that mode we get all sorts of vacuum fluctuations. And so as the loss increases, it's as if we're simply adding noise to our experiment. Okay, so the lower the loss, the better. The other thing to mention is that if we're integrated on a small chip, we're avoiding all sorts of things like phase fluctuations. These are very important in Homodyne detection, where the phase of the local oscillator plays a very significant role. And finally, a bit of a pot shot at the superconducting detectors. These are also functional at room temperature, all right? So we're talking about sort of standard equipment rather than complicated cryosystems. All right, so Akira, you'll have to forgive me for using this photo, but I think it proves a nice point here. We have a picture of Akira's lab, which some of you may think this looks like a mess, but to me this is a work of art. So this is a fantastically complicated experiment, all made out of bulk optics, and these are all moving around. And so the idea is that we'd like to attempt to turn this type of experiment into something that looks a little bit more like that. And again, as I mentioned, the reason is high phase stability. And also something which I didn't mention, which is that in integrated photonics we have this nice scalability and simultaneous fabrication. So now I know that if I make one device, it's very likely that the device that was made hundreds of microns away is going to be very similar. Okay, so core components here are a very, very brief tour of integrated photonics. Coupling on and off chips, we have things called grating couplers. This essentially diffracts the light out of the plane of the chip and allows us to couple to the chip using standard fibers. Problem with these are very lossy. Okay? We have delay lines, beam splitters. So the beam splitters are actually look something like this: a directional coupler where we sort of evanescently couple two waveguides, or perhaps a multi-mode coupler where through some sort of interference effects we allow light that enters one waveguide to be split between the two output waveguides. We have phase shifters, both thermal phase shifters, so essentially this is just changing the temperature of the silicon. And silicon has quite a large thermal optic coefficient, so this allows us to enact phase shifts, albeit at a slow rate. We also have active phase shifts that use carrier effects and dopants in silicon to enact fast phase shifts. So detectors, that's essentially what this talk is about. And finally, we have things like sources and filters that we heard mentioned before in the context of these ring resonators here, where through nonlinear effects, we can generate single photons and things like that. Okay, so there's a whole host of different material systems that you might want to investigate in integrated photonics. Today, I'm only going to talk about silicon, okay? And the reason for this is because this is the fabrication process that I have available to me, essentially. So as we'll see, there's a whole bunch of reasons why silicon is great. These are sort of the standard taglines that we say over and over again. But really the important ones to me today are that we have well-established processing techniques. This is simply because I would much rather focus on foundry services than have to pay millions of pounds to have access to a fabrication facility. There's also large-scale manufacture. So by large scale, really what I mean here is that I can fabricate many photodiodes next to each other. I haven't mentioned photodiodes yet, but you'll see this is essentially the core of the technology. I can fabricate many photodiodes next to each other. Finally, we have maybe the possibility of integration of electronics and photonics. So we may have some detectors, and then we're hopefully thinking about integrating electronics along with these. And finally, we have high confinement, and this leads to efficient detectors. So all of our detectors are really evanescently coupled detectors, as we'll see. Okay, so this was sort of the very quick and broad overview of why I might care about an integrated Homodyne detector. But what exactly is a Homodyne detector? So at its core, a Homodyne detector is simply a phase shifter, a beam splitter, and two classical photodiodes. Okay. So here you can imagine shining a very strong in the sense that it's visible in some sense. Laser beam on this beam splitter, and what happens is that the laser, this is a balanced beam splitter, so the laser is an equal intensity of light goes here and goes here, and so if we take the subtraction between the two photocurrents of these two photodiodes, what we see is that we have a current that's essentially a current that's zero. Okay. But actually, quantum mechanics tells us something slightly different, which is that it's zero, but of course there's some distribution here. It's not exactly zero all the time. This has some distribution, and this is the shot noise. So essentially, this is each photon, when it hits the beam splitter, has to decide whether to go left or right, and each of these photons will make a slightly different decision, and so these statistics leads to this sort of noise. Okay. So if we plot a histogram of this noise, we get some nice Gaussian random distributed variable. And what happens now? So right now we know that we have some vacuum perhaps entering into this part of the beam splitter. What happens if, for example, we instead, did this thing stop working? Oh, there we go. If instead we were to put a single photon field incident on this beam splitter, well, now we have this single photon field interfering with the laser field. And actually, if the amplification in the Homodyne detector is enough, I haven't drawn the amplification here, we can see this effect in the interference. You actually get this splitting of this photocurrent here. Okay? So this is a significant effect, and in fact, this is quite general. Regardless of what field you have entering the beam splitter here, we can use the properties of this interference to reconstruct the state of the electromagnetic field, the quantum state of the electromagnetic field. So this is a fairly general technique, and this allows us to do all sorts of really interesting experiments. I think we've seen quite a few examples of these today already. What does it look like in an integrated context? Well, this is the experiment we've done here is 2 single-mode waveguides, a multi-mode interference device, which acts as our 50-50 beam splitter, and finally 2 integrated photodiodes, which I'll talk about in a second. The optical chip is then electrically coupled to a PCB, which, as you can see. So down here is this tiny rectangle of black, which is the silicon chip. And then over here we have a large amount of classical electronics. So the idea is that eventually we can have all of these on the same chip. Let's take a slightly closer look at the photodiodes. So these are selectively grown germanium on top of silicon. They are, as I mentioned before, evanescently coupled detectors. So the germanium is grown on top of the silicon waveguide. This is an example of a ridge waveguide structure here. So we have the germanium is grown on top of the silicon, and the silicon has been doped. So it's p-doped silicon with intrinsic germanium grown on top, and then finally you n-dope the germanium on top of that, and it gives you a PIN structure, which gives you your photodiode. All of the absorption happens inside the germanium, and as I said, this is evanescent. Okay, so these are quite good. They're very, very small, which actually turns out to be a large advantage for photodiodes. One is that their speed is quite fast, so without too much work, you can get up to 40 gigahertz. The quantum efficiency with the photodiodes that we work with is limited to about 80%. This is not intrinsic to the photodiodes. The problem is with working with foundry services is that they're all from the classical photonics industry, so they don't actually care about the quantum efficiency of their photodiodes. As long as it's above some threshold, it's fine. Really what they care about is the speed, which actually, as it turns out, is not too important for quantum Homodyne detection. Okay, so as I said, this looks something like this in the lab. You can see a microscope image of it there. All right, so we have to characterize this Homodyne detector. There are several things that are several properties that are very important for a Homodyne detector to have. One is that all the application electronics, as well as the photodiode dark current, is going to have some electrical noise. So what happens if we scan the local oscillator power and observe the Homodyne detection? We sort of observe the variance of the Homodyne detection signal. So as we scan the local oscillator power, so just look at the blue dots for a second here, we see that we are sitting at the electronic noise level, and as we increase the local oscillator power, eventually we start to increase the variance. Okay? So at this point, the shot noise is greater than the electronic noise. The electronic noise is uninteresting, it's just extra noise in our system. So in a very real sense, the size of the quantum signal that we're going to be measuring and using to determine our quantum state is going to be proportional to the variance of this signal. So it's good that the variance of our shot noise is much larger than the background electronic noise. And in this case, it's about 11 dB, which is not so bad. We measured the internal loss of our detector. So this is including the loss in the waveguides and the multi-mode interference device, and then finally also the photodiodes. So in total, there was a loss of about 36%. If you include, so remember I said that loss can be modeled as noise. As it turns out, this noise also can be modeled like loss. So what this means is that the electronic noise actually places a limit on the efficiency of our Homodyne detector. And what this means is that although the internal loss is 36%, the total quantum efficiency is not 100 minus 36, it's actually 59%. Okay, so it's slightly lower. But still quite good, it's still above this sort of 50% classical bound that we're interested in. Also, the Homodyne detector, this was quite a pleasant surprise. The Homodyne detector is quite fast. It's about 150 megahertz fast if you look at the spectral amplitude. And so the reason this was surprising is because we based this detector actually off of one of Alex's designs. And it uses all the same electronics. The only difference is the photodiodes. And in fact, the reason why it's faster is simply because the photodiodes are smaller. So they have a smaller capacitance. And this sort of forms a bit of a low-pass filter with all the amplifying electronics. And so if you have a lower capacitance, you have a faster detector. So this was quite nice. And we measured also something else called the common mode rejection ratio. But suffice to say, it's quite high. All right, so what can we do with this Homodyne detector? At the current state of the art, we don't quite have the ability to be measuring things like squeeze states or single photon states. But the first thing we thought of, well, is let's not measure any states at all. In fact, we have a Gaussian random Gaussian distributed variable, as I said before, and the source of this distribution is not anything classical. It's not the electronic noise, as I mentioned before, but in fact, this is the shot noise. This is really whether each photon decides to go left or right at the beam splitter. So we can use this random variable to generate random numbers. 5 minutes, perfect. So we can use this random number to generate random numbers. We can take our distribution here and split it into any number of bins that, as we like, as long as they're not too small enough so that they're compared to the electronic noise, for example. And then we can sample this Homodyne detector at slightly above its bandwidth. We get away with about 200 megasamples per second. And so it turns out that we can split this into approximately 6 bits of entropy. So we get about 6 bits per sample, sampled at about 200 megasamples, gives us 1.2 gigabits per second of random number. Okay? And this is after some post-processing, right? So these bins are all equally sized, but they're not all equally populated, and so there's some bias in the random number, but we can get rid of this with classical post-processing. So not a real-time quantum random number generator, but in principle it's possible to make it so. All right, so I said we were not quite at the point where we can be measuring single photon states and squeeze states, but we can in fact measure a quantum state, albeit it's the most classical quantum state, the coherent state. So what we do is we take our CW laser, which acts both as the local oscillator and as the state that we're going to be characterizing, and off chip we attenuate it quite a bit, and then also phase modulate it so that we can do some sideband detection. The problem here is in future applications, we'd like to generate the state and detect it on the same chip to get this nice phase stability that we talked about before. The problem is we're not quite doing that yet, and so this junction here moves around, and so we have quite a lot of phase instability. We do sideband detection to get around this. So we measured some states. We have an average of a half a photon, 1 photon, and 1.5 photon. And the fidelities of these are quite high. Okay. So, very quick talk. I think I will briefly mention some future directions. So right now we're using sort of standard fabrication facility photodiodes. These are nice in that they have a relatively high quantum efficiency. We'd like to be able to get this higher, so we're currently looking at designing our own photodiodes, albeit still through a foundry process. So we'd like to design some higher efficiency detectors, really push the limits. Characterizing on-chip sources of non-classical states. This is single photon states and squeezing. This is a work in progress. And as well, Homodyne detection as a characterization tool for these multi-mode interferometers we have. So as I mentioned, we can make a photodiode or make a Homodyne detector, and we can stamp one next to another, and we can be relatively sure that these two are going to be very similar. So this means that we have the ability to stamp lots of these down and characterize maybe larger, more complicated processes. All right, thank you very much.
Thank you, Dylan. Do we have questions from the floor? So I have 2 questions. Thank you. So first, do you have any possibility to control the balancing of your beam splitter? Make it exactly 50%?
So very good question. In general, we do, because usually we wouldn't rely on an MMI to give a good balance, right? So these MMIs are pretty good in that we can usually guarantee to within 1% or 2 that they're 50-50, but that's not quite good enough for Homodyne detection. So in general, we'd be using a Mach-Zehnder interferometer and then actively tuning the interferometer to have equal splitting. In this case, we ended up using the wavelength of our pump to tune it because it's sensitive to the wavelength. So.
Second question is, in your random number generator, you say you generate 1.2 gigabits. Does that include the contamination of the electronic noise?
Yeah, so this is after we have sifted the raw data that we've gotten out of it. The 6 bits per sample, I should have mentioned, is after we've sifted through the raw data.
So that's assuming that, that an enemy is controlling your electronic.
So in principle, we could allow for an enemy to control the electronic noise. This is why you always have to do some sort of pre-calibration step to figure out how big the electronic noise is So what I can guarantee is that the random numbers that we obtain at the end of the day are completely uncorrelated with the electronic noise. But this is because we've measured how large the electronic noise is and then done some sort of hashing to get rid of it.
The Gaussian distribution in your random number sort of generator, that's a histogram of the numbers of times of occurrence. So why have you split it up in equal widths? Or is that just a simplification?
Yeah, so it turns out to just be simpler for the algorithm. This is the hashing algorithm that we use.
Just 111s as you get.
Yeah, it's true. So you end up throwing out more data this way, but it ends up being simpler in the end for us to use.
You pushed one of my buttons.
Oh dear.
You said that you're sure that the electronic noise is correlated from your quantum knowledge. But you pass it through a digitector, right? Can you repeat the question?
Sure. Okay. So I've pushed one of his buttons, and that I said that the random numbers at the end are uncorrelated with the electronic noise. But he's pointed out that I've passed it through a digitizer,
Which is a highly nonlinear device and can correlate just about anything.
Okay. This is not something I thought about. Yeah, off the top of my head, I'm not. We'll talk about this after. This is actually great. Thanks.
What's the dark current of the PG you used in your experiment?
Oh, that's a good question that I'm not sure I know off the top of my head. It is so. I mean, I know that at least it's sufficiently low such that this experiment works, right? Because the dark current would contribute to electronic noise, and so this should be smaller. Do you happen to know? I'm looking at one of my students. Sorry. Okay. Sorry. I can certainly look it up.
Okay, I think perhaps there'll be more questions over drinks on the ship later. Let's thank you.